Okay, is it better? Do they see my screen? Okay, so I'll start over. So welcome to this third course of this module of this course, Electronic Structural Simulation for User Communities at Large-Scale Facilities. My name is Giovanni Pizzi. I'm a group leader here at PSI. And today we will start with a practical guide to DFT simulations. In particular, we will have, let me just remove this. Is it possible to remove this? We start with a practical guide to DFT, to technical aspects that you need to know in order to be able to understand a bit the naming parameters of a simulation. And then we will move on to kind of hands-on, where we'll be able to try AiiDAlab and AiiDAlab Quantum Espresso app. Maybe you can unraise the hand because it doesn't appear. And just so you know, in the fourth module, you will have a continuation of the hands-on, more specific to workflows which are relevant for large-scale facilities. We will look into phonons, first into inelastic neutron scattering, and then into infrared and Raman spectroscopy. We will then look also into simulation of Bader charges and of muon resting sites and spin relaxation function of muons. We also get a brief explanation on what you can do to continue after this course, because we give some HPC resources, some resources online for the next 3 days. But then we'll also tell you how you can continue running either on your laptop or if you are a PSI, we also provide a machine for PSI users. But we'll discuss this more later. Just before I continue, in addition to me, a lot of work and what you will see has been possible thanks to the whole team of developers of AiiDAlab. In particular, here you have Xing, Miki, and Timo. On Wednesday, we will also be Andres from EMPA here, and Dan is online on Slack to help for the questions. He's been already very active also for the development of the app. Today is at a conference, so he cannot be here, but he's helping us remotely. So let's start with the practical part. So first of all, first few slides really will be very quick because you should all know about it. So first of all, we are going to consider crystals in periodic boundary conditions. So once you consider a periodic system, they can be described by 3 vectors in real space, here called A1, A2, and A3. Let's see if this works, yes. And this define a lattice of points in space. And as you probably know, there are only 14 possible lattices, Bravais lattices, which are possible, going from body-centered cubic, simple cubic, face-centered cubic, orthorhombic, etc. Because your system will be periodic, you're going to describe periodic systems. The Hamiltonian itself is periodic. And therefore, we can apply Bloch theorem, which tells us the wave function has a very specific form. It's a product of a periodic part, U, which is the same periodicity of your lattice, times a phase, e to the I k r, where k is a quantum number. It's a proper quantum number of the system. And essentially what you have is that this k is essentially modulating your wave function between neighboring cells. As you might expect, now the square modulus of psi is your charge density, which is an observable. So the charge density is periodic. But the wave function itself doesn't need to be, and this is enough for obtaining a solution of a periodic Hamiltonian. Once you have your Bloch theorem, and so k is a good quantum number, what you can do is to make plots of what's called the band structure. So as a function of k, this quantum number, you can plot all the possible energy levels at k, and you get a plot which looks roughly like this. In order to, however, do this plot, we have to first understand what's a reciprocal lattice, right? So in order to understand this, we have this form from Bloch theorem, which tells us that psi is a periodic part times phase. And let's say for a very simple model, we have really a one-dimensional system, lattice parameter is A, and we want to understand which k values are possible. Okay, can any k value be a good quantum number, or there are some k values which are not allowed or they're equivalent? And I won't go through the math. You have it here. You can just do a little rewriting in a different form, but essentially you get a relation that your wave function for wave vector k and your wave function for wave vector k plus g are the same, so this phase is the same, when g is a multiple of 2 pi over a, where a again is your real space lattice parameter. Therefore, we discover, for instance, that in one dimension, so if I do, if I consider k equal to 0, or k equal to 2 pi over a, or k equal to pi phi over a, these are all describing the same quantum number. So I can limit myself only to minus pi over a to pi over a, and that's enough for my for describing my system. And these G vectors are what form the so-called reciprocal lattice, which again is a vector, as you see, of points in a different space. The units are different, it's 1 over length. In 3 dimensions, it's the same, just that the relations are slightly more complex. But essentially, you have the same relationships, just at this time, you have a more like vectorial relation. So I'm struggling a bit with my mouse, it's okay. So you have a kind of vectorial relation where essentially if you have a vector, a matrix of your lattice vectors, the transpose inverse will give you the matrix of the reciprocal vectors in 3D. And they also form a lattice. So in real space, you have a simple cubic lattice. This, for instance, will form a simple cubic lattice also in reciprocal space. You can write down these red expressions if you want to obtain these vectors explicitly. And again, as I said, if it's simple cubic, you get simple cubic. But it's not always as trivial as you might think. If you probably know, if you have an FCC real space lattice, the reciprocal lattice is BCC and vice versa. If the lattice is orthorhombic, also the reciprocal lattice is orthorhombic, so the angles remain 90 degrees. But if the angles are not 90 degrees, also there the angles in real space and then the reciprocal space are not the same. You have to compute this using these formulas, and you can easily verify these relationships. Now, one important note is, and again, apologies for those in here that I'm not sure I can. Okay, maybe I can do this. Okay, that's better. Yeah, also close this. So you can describe a lattice in multiple ways. Okay, the same lattice can be described, for instance, using 2 orthogonal vectors, in the specific case of a square lattice in 2D, and then you can obtain the corresponding reciprocal lattice vectors. But in a very alternative way, an equivalent way, you can describe the very same lattice using now different vectors. Okay, these are perfectly valid choice of vectors. It's a linear combination of the previous ones. If you repeat periodically the points here, you obtain the very same lattice, but this gives you a different basis set essentially. And if you go in reciprocal space, also in this case, you get a different representation, different basis set, different reciprocal lattice vectors for the same lattice. So the important physical quantity, if you want it, which is the lattice, is the same, but the basis set you can use is different. For this reason, it's interesting to introduce a concept of the first Brillouin zone, which essentially is the set of points in reciprocal space which are closest to the origin than to any other point. So in this case, for instance, so this is the origin. These points inside this blue square are closest to this point than to any other one. And this is my first Brillouin zone of a 2-dimensional square lattice. It's very easy. And let's say the advantage, so there are numerical advantages of using one or other description or the other description. In particular, using the primitive reciprocal cell, so the orange one here, it's computationally easier because you just have to put numbers between 0 and 1 to make a kind of grid in this region if you want to sample this region with a finite number of points. So in codes, typically, you would use this one. But in reality, when you want to look at it, when you want to understand it, when you want to compute band structures, you will most often use the Brillouin zone because it typically has the same symmetries of your system. So if you have a tetragonal system, also the Brillouin zone will be tetragonal. It will kind of keep the symmetry of the system. While and also is kind of more unique, is the same, it doesn't depend on your choice of vectors. Instead, the primitive reciprocal cell will depend on the choice of vectors you made. In 3D, so in 2D, in this simple case, the Brillouin zone is square. If you go in 3D, the shapes are a bit more complex. They are kind of typically objects with truncated faces. But the typical common ones we probably, for sure, you have already seen are, for instance, the FCC and BCC reciprocal Brillouin zones, which have this kind of shape you see here. So again, we go back to our problem of plotting a band structure, which again is very important, as I'm sure you know, for obtaining or looking into energy gaps of materials, to look into effective masses, etc., for transport. And in 1D, it's easy because we just take our one-dimensional reciprocal space, and we just compute bands. There are many bands at every k points, indexed by index n. But if you're in 3D, we have to do this plot as a function of three-dimensional variable of any k vector in the Boolean zone. So how do we do it? Well, the solution is to use band paths. So you essentially define points in your Boolean zone, which have high symmetry typically. So the center, which is always called gamma. In the case of, for instance, here is silicon. So on FCC lattice, you have L, which is the center of this hexagonal face. You have X, which is the center of the square face, and so on. You just define paths and just compute the bands along this path, with the idea that along those paths, you have higher symmetry, so many of the degeneracies might be there, and you hope to see the most relevant aspects of your band structure. In this way, you end up with plots that you all have seen in publications, where essentially this means I'm moving from L to gamma, then I'm turning and going in a different direction from gamma to X, and so on and so forth. This is what we will compute today later in the second hour. Of course, for silicon, probably you all have seen the paths. You kind of go in the literature and you know what X means, what L means, etc. But if you never do it, well, the good thing is that on our platform Materials Cloud, we developed a tool called SIGPath, where you can just upload a file of any crystal structure. And this will compute on the fly your Boolean zone. You can visualize it. You can get a suggested path that you might want to compute. You get the coordinates of the k points. It also computes actually the symmetry, the space group symmetry of your crystal, all in your browser. So you just upload a structure, you get it, you can download it. And at the bottom, you can even download a template input file for Quantum Espresso, CP2K, and a few more codes. So you don't have to write down and derive the names of these points. Luckily, this is now something you can just click on the web and use. So this was just a very quick introduction about periodic boundary conditions. Now we go into more technical aspects of how you actually run a DFT simulation. The first thing is that you have to convert a differential equation. You saw in the last lectures that in the end you have to solve something of the form operator Hamiltonian times psi, your wave function, equal to energy times psi, a kind of eigenvector, eigenvalue problem. But this is still a differential equation, right? H contains the kinetic term, which is a second derivative, and so on. So you have somehow to write it in a numerical form that you can solve on a computer. And the way is to define a basis set. So essentially, you represent your wave functions as a linear combination of some set of basic elements that you think are representing very well your problem. Typically, that's not necessary, but typically in what we will always see, we always define and use orthonormal basis sets. So vectors have norm 1 and they are orthogonal between each other. And if you use so you expand your wave function into a known fixed basis set, your unknowns become complex coefficients in front of each of these basis set elements. You just can compute the bracket of your Hamiltonian, and essentially what you do, you convert your differential equation into a linear algebra problem, a matrix diagonalization, because essentially here you have coefficients, which are just the Hamiltonian matrix elements between your basis sets. And this is exactly a eigenvector problem, where this is your Hamiltonian, and you're trying to solve for a long list of complex vectors, complex coefficients. This is an operator times vector equal to E times vector. In the end, what you do, you just compute this Hamiltonian on the basis set. You give it to a computer. You say, please diagonalize it for me. And the computer will give you both the eigen solutions, the eigenvectors, so the wave functions, and the corresponding energies. So which basis set can we use? This depends a bit on a number of aspects. The type of problem you're trying to solve, but also some computational aspects, how precise you want to be versus how fast you want to be, okay? Because this calculation can easily become very complex. For molecules, typically one tries to use a very localized basis set. For instance, a set of Gaussians centered on the atoms in your molecule. And you see, Gaussians are, the reasons is that Gaussians, you can do easily integrals and compute these matrix elements between Gaussians at different sites analytically. So it's very fast to compute these integrals. And already, you know, with 3 Gaussians, for instance, you can already approximate, at least visually, qualitatively well, e to the minus alpha r, so something which is a kind of a cusp here. So, you know, it's a good basis set if you want to, this would be a solution of a hydrogen atom, for instance, okay? So just with 3 Gaussians, you can get already, the sum of these 3 would be the kind of dashed line you almost don't see, which is on top of the analytical solution. So this is very good for molecules, because you can really have a basis set which is only there, and with few basis set elements, you already have a reasonable accuracy, and you can compute things quite fast. For solids, one can also do Gaussian basis sets, but what we will see in this course, and it's pretty interesting and effective, and we'll show in a moment why, is to use the fact that you are in a periodic system and use a periodic basis set. And the simplest periodic basis set you can use are plane waves, so cosine and sine functions, which have the same periodicity as your unit cell. It's not the only possible choice. There are other ones which we'll not discuss here, just so you know. But I will just want to discuss plane waves for a moment, because that's what we'll see in quantum espresso. In particular, the idea is that you take a periodic function. Let's say this is your u and k, the periodic part of your wave function. And let's say this is really periodic, that you have this function and this repeats periodically in space. What you do, you just sample it in a number of points in a grid. If it's in 3D, it would be a 3-dimensional grid. And then you just do a Fourier interpolation of the points in between. Okay, you just sum sine, cosine functions with different frequencies up to a certain frequency. And of course, the more oscillations you have, the higher the frequency you have to have in order to correctly reproduce this curve accurately. And the nice thing is also that essentially, in order to compute it, what you're doing are just Fourier transforms. So you take your periodic function, you sample it on a grid. To obtain the coefficients of your plane waves, you just have to do a Fourier transform. And there are very efficient algorithms, fast Fourier transforms, that you can run on your computer to go from one space to the other. So in the end, again, to summarize again, we have our wave function, what we want to solve. We have Bloch theorem, so we know we can write as a periodic part times a phase. And for this periodic part, we just expand it in plane waves. And essentially, this means that you have to sum, okay, here I have an error, sorry, this should be G. You have a sum of G of e to the I GR, so this will be the plane wave, times some coefficients, some complex numbers. Once you know these complex numbers, you know your periodic part, and essentially you know also your wave function. Now, the first time one sees this might get a bit confused. What's the difference between k vectors, g vectors? What are they representing? So let me try to summarize again in one slide the difference between them. So k points, what are typically called k, so both k points and g vectors live in reciprocal space, okay, a unit of 1 over length. And k points are typically chosen inside either the primitive reciprocal lattice or the Brillouin zone. And any points outside is equivalent. These are good quantum numbers, and they represent a quantum number to determine your solution, and essentially determine the long wavelength behavior of your solution. You solve it in the unit cell, you get a periodic part. And once you know what happens in a unit cell, you can know what happens in the next cells by just multiplying by this phase, given by e to the IKR. And this is valid whatever basis set you have. That's a property of periodic systems. In the specific case of plane wave basis sets, then you can expand them. You have to represent this wave function, this periodic part of the wave function, in some basis set. And as we said, we don't use localized basis sets here. We use plane waves. Essentially, you can write this as a sum of plane waves with high frequency. You have to have the main frequency. You can have twice the frequency, 3 times the frequency, etc. And these are the frequencies are essentially the G, this is the reciprocal lattice points. Okay? Every point is a G vector, and this determines essentially the frequency of a wave which has the same periodicity of your lattice. So again, k points inside the Brillouin zone, quantum number. G vectors are essentially the reciprocal lattice points and determine the plane wave expansion of your periodic part. Once you have a basis set can be complete if they're infinitely large. But of course, you cannot write an infinitely large basis set on your computer. So you have to stop at some point. For instance, if you use Gaussians, you can say, I represent my solution with 5 Gaussians, and that's it. And I just have to find the coefficients. In plane waves, you have to decide how many plane waves you want, the number of plane waves. Or if you want, what is the highest frequency you can represent. So for instance, if you have a charge density which is very peaked in a point, you will need a lot of frequencies to represent this very sharp peak. If your charge density is very smooth, you don't need so many. And you have to essentially give a number, say my calculation in the input, you have to say I want so many plane waves. Of course, one way to say it is I want 1,000 plane waves. That's one good way to say it, but it's not very nice for one reason, that essentially the distance between G vectors, if you remember from the previous slides, okay, goes as 2 pi over A. So it depends on the size of your system. So if you have a very large system, the distance is very small. If you have a small system, the distance is very large. So depending on the system, the number of points is a variable which is harder to capture. So what you can actually do in the end is do something different. You say, okay, I want to have frequencies only within a sphere in reciprocal space. So if you have very high frequencies, I don't want them. If the frequency is small, I want it. And instead of defining the radius in units of 1 over length, what you actually do is to convert it into an energy. Okay? If these were plane waves, real electronic plane waves, their energy would just be h bar g squared over 2m. So essentially, you can just write the energy of these plane waves, and you say, I want all the plane waves which are within, whose energy is within an energy cutoff. And that's what will be what we call as cutoff in the next, when you will see later in the presentation. So essentially what you say is, I want to define a radius in reciprocal space of all the wave vectors I want to keep, all the G vectors I want to keep, which determines the highest frequency. So 0 would be constant. The first point would be one single big wave. A large G vector means a lot of oscillations in a period. And instead of defining the radius in units of 1 over angstrom, you define the radius in units of an energy, using essentially this relation. Just take the value, square it, and multiply by a coefficient. This gives you an energy in electron volts, Rydberg, or any other energy unit you want. So now we start seeing, okay, why plane waves? Okay, I told you how you define them. I told you what are G vectors, but why is this a very interesting basis set? Well, the first thing, which is actually very important for, again, if you remember before I told you for molecules, often you want to use Gaussians. And the reason is, for Gaussians, you can easily compute integrals, okay? So the derivative of a Gaussian is still a Gaussian. You can do integrals very easily. In this case, the reason is that if you want to compute the kinetic term, so the kinetic operator is a nabla square, so the second derivative, well, it's very easy because now your second derivative, every derivative is just moving out here e to the e times k plus g. So the second derivative is just multiplying with minus k plus g squared. So in reciprocal space, derivatives become very simply multiplication by a number. Okay, very easy. I don't have to do derivatives anymore. And so here is a summary of the main nice properties of plane waves. Number one, I can systematically improve them. Okay, for sometimes with other localized basis sets, you don't know what other basis set you have to add. For plane waves, you just keep increasing this radius, keep increasing this cutoff. At some point, will be converged. Maybe very expensive, but will be converged. So you have a systematic way to check if you're converging your results with the finite basis set you chose. Another interesting thing is that the basis set depends only on the cell. Doesn't depend on where you put the atoms, which means that you don't have what's called a Poulet term in the forces. If you have a basis set which depends on the position of the atom, when you move an atom, the basis set also moves. At least in practice, you have to correct the effect this will give on the forces. When you compute forces, you're moving an atom essentially and computing a derivative of the energy with respect to the position. That's the definition of a force. Okay, energy minus derivative of energy with a little displacement. This derivative, if you just do it naively, will be wrong because the basis set is moving with you. And you have to correct it in codes which have a localized basis set. In a plane wave basis set, you don't have this problem. Whatever you do the derivatives, and they're correct. And then the third point I was mentioning derivatives, second derivatives are very easy. And in fact, in these codes, you have to compute a Hamiltonian, t plus v multiplied by a wave function. And typically what you do, you keep the wave function stored both in real and reciprocal space. Essentially, you have two vectors and you do Fourier transform between them. When you have to compute the kinetic term, you just do it in reciprocal space and multiply by k plus g squared. When you have to compute the real space potential, is v times psi, is a local potential. You just do it in real space. And then you do a Fourier transform to sum them. One problem that we'll solve in a moment is that, however, if you want to go to very heavy elements, lead or rare earths, etc., these are orbitals which have, we show later better, 1s, 2s, 3s, 4s, a lot of orbitals, and the 1s are very close to the nucleus. So if you don't do any trick, you would need a huge cutoff, a huge number of plane waves, so huge matrices in memory, in order to compute these quantities correctly. And we will need to use pseudopotentials in order to make plane wave basis sets effective. This will be part of, we'll tell you in 20 minutes. Okay. Maybe questions until now before I go to K-points? No? Okay. So we started from lattice parameters, reciprocal space. We discussed how to discretize basis sets. There is one more thing we have to do now, because all our quantities are defined as integrals in reciprocal space. And as we said, since the quantum numbers are only in the primitive, in the first Brillouin zone, we can just do integrals in the Brillouin zone. Typical example is the charge density. The charge density is essentially the sum of the square modulus of your wave functions summed over over the whole space. So actually, it's an average 1 over volume. So this is already discretized in this form. So it's an average of these objects summed over all the occupied bands. So you have valence and conduction bands. You only sum where electrons are. Numerically, I don't want to compute an integral. I don't know how to compute it. I will typically convert the integral in the reciprocal space or in the Brillouin zone with a sum over a finite number of k points. So I have another numerical aspect. I have to decide how many k points I use to do my integrals. And the most common way is not the only way. There are others. There is the tetrahedron method, which in interest of time I will not discuss today. But the most common way is what are called Monkhorst-Pack meshes, which essentially mean you take your, in this case, again, as I told you before, numerically it's easier to consider the primitive cell, not the Brillouin zone. And I just divide it in a regular grid. Okay, if I tell you I want a 4x4 grid, I just divide my grid into 4x4 squares or whatever shapes, and they take points in this grid. Again, 1, 2, 3, 4. These I don't need to put because this is periodic vector, so this and this point are the same. So this is a 4x4 by 4 in 3D, unshifted grid, because it includes also the origin or gamma. Gamma is the name of the origin in reciprocal space. You can also shift it, okay? Shift it by half of the grid. So essentially you take the points in between here, in between here, in between here. It's still a 4x4x4 grid, and it's a shifted one. Just be careful if you use different codes, the definition of shifted depends. Sometimes people, depending if it's either even or odd, because this was the original definition of Monkhorst-Pack, define this is shifted, this is unshifted. Let's say for us in Quantum Espresso, if in case you want to look in the input, the way you write, I want a 4x4x4 grid, including gamma, is 444,000. When you have 000, gamma is included. If you want to shift it, so it doesn't include gamma, in all three directions, you would put 1, 1, 1 instead. This can be only 0 and 1 here. Just means shift or unshifted, while these are the density of your grid. One very important thing to know, because you will see in the output, you don't have luckily to do anything, you just have to be careful, let's say the code does it, is to use symmetries. So if you have a cubic system, for instance, you have a lot of symmetries. You can have a plane symmetry, you can have a 90-degree rotation symmetry, 180-degree rotation symmetry, and so on. Properties, the system goes into itself when you apply these symmetries. So also in reciprocal space, properties on different k points can be related by symmetry. For instance, the energies, the wave functions can be the same if they are scalars, can be the same after rotation if they are vectors. Therefore, if you want to, when you have to do this integral, you have to sum psi square modulus of psi and k, for instance, over all these points, you don't need to compute the points, the wave function, diagonalize the matrices at every point. If you have symmetries, for instance, let's say you have let's say this is a mirror symmetry, you know that the properties here and here are the same. So you can just compute properties in what's called a reducible wedge, and you know that properties on this side are the same, and you save a lot of computation, okay? For instance, if you do a 9 by 9 by 9 grid in a cubic system, that you will do later actually for gold, this will be 729 points. In reality, the code, thanks to symmetry, only computes 85 points. So, an order of magnitude less calculation in the end. This is very important. Instead of that taking a day, it takes 2 hours. It's good. The important thing to know, however, is that every point now has a weight. Before every point, you have to do an integral, right? So you just sum the values on these points, and every point has a contribution which is the same. Depends on essentially the amount of volume around it. Now you have to put a weight which can depend on the points, because for instance here this blue point counts 2 because this and these are the same, and so when I count it I have to count it twice for this and for this. But if I have a point on the mirror plane, for instance, this only counts for itself. There is no other point. So in this case the weight is 1, is half of it. And then you can normalize it to 16. Okay, so essentially, whenever you look in the output, you will see I only compute 85 points, even if you put in the input 9 by 9 by 9. And in addition to the coordinates of the k points, you will see a weight, which essentially is typically, okay, if you have, this would be 9 by 9 by 9, but here it would be 1 over 8, 1 over 16, etc. The code, when you put the input, it will compute the symmetries for you. It will understand how many points it needs to do. It will show you which symmetries it found, and it will do all of this for you. But it's important to know because, for instance, if you put some numerical noise, symmetries are lost and the calculation starts to cost a lot more. And there's also less, typically there are other issues which can arise numerically when you don't use symmetries. So a reminder now, because now we are going to a slightly more interesting technical aspect, which is about metals. But before we go into this, I want to remind you how the simulation happens. This is what Nicola already showed last week. So you first have to construct an external potential. No? That's how you initialize your calculation. Again, you don't do it yourself. The code will do it for you because you will give the coordinates of the atoms. And the code knows, okay, I have iron there. Okay, I want to put the potential of an iron nucleus here. I have oxygen there, etc. So in here, typical external potential really means the nuclei, the position of the atoms. Then, okay, you have to choose some parameters, basis set, k-point sampling. You have to start with initial electronic density. Typically, you start from something, maybe contribution of atomic-like densities. And then using this, you use Kohn-Sham equations. You obtain an Hamiltonian. You write it on a basis set. You diagonalize the matrices. And you obtain a new charge density. You obtain new solutions, new psi. Square modulus, you sum over k points. You get a new charge density, and you iterate. And you do this until your charge density or your properties are converged. So essentially, you do another iteration, nothing happens. You get the same solution. This works typically, and it's not, unfortunately, it's not, there is no guarantee that these iterations do converge. And that's how you will see it can happen. That you run your DFT simulation, and the code tells you, I didn't converge. And then you have to try some tricks. I will mention in a moment. There are some numerical tricks, numerical algorithms to try to improve this. However, the problem becomes very severe, and you wouldn't be able to solve it without smearing, which I'm going to say in the slide, for metals. And the reason is the following. While for insulators, you have valence bands which are fully occupied, and conduction bands which are fully not occupied. So your sum I was showing you before, this sum here, is over all occupied states, and you have fully occupied states and fully unoccupied states. So it's relatively clear what you have to do. When you have a metal, so you have bands crossing the Fermi level, and you have a discrete basis set, okay, discrete k-point sampling, sorry. There can be, during iteration, slight changes and bring maybe some k-points below or above the Fermi level. Let's say this is your Fermi level. You do an iteration, you get this. It's an approximation, of course. Then the next iteration somehow brings you here. So you now start counting more points. And you have only few. I mean, you have to remember we are considering tens of points, not millions of points. Therefore, this starts creating very often an instability. and you never converge. Okay, you keep switching between different solutions, you never get to a solution. And so how do we solve it? And again, one important thing to remember, DFT simulations are done at 0 Kelvin. Well, you add a kind of fictitious temperature or smearing, which essentially is what you would have if you had a temperature. You take a occupation, at 0 Kelvin would be 0 for all the conduction states and 1 for all the valence states, or times 2 if you have spin, but I say, for simplicity, say 0 and 1. Instead, you replace it with something which has some smearing. Fermi-Dirac is a very good valid choice, but you can use other shapes. This is really a numerical trick. It's not a way to introduce temperature in your simulation, okay? But thanks to this, now, when you go between here and here, you don't go from completely not considering it to jumping down and completely considering it. Maybe you go from considering it with a weight of 0.6 to 0.4. So you have a continuous function, and this can help convergence. So I will try in the next slide to show you 2D examples. So it's very clear what I'm speaking about, I hope. But first, a few comments on smearing. So number one, smearing is a fictitious temperature. Again, don't think you're simulating a real temperature. Also because typical values you would put can be of the order of 0.1 electron volts. If you convert this into temperature, this is thousands of Kelvin. So you're not trying to simulate a 1000 Kelvin system. Otherwise, things would melt. We are just using a trick to facilitate convergence. And as long as the results are correct, we are happy. And the question if results are correct is important, because now, while usually we would compute the total energy of our system, since we are in the end introducing a kind of temperature, what we're actually computing and minimizing is not anymore a total energy, but becomes a free energy. No? Free energy is E minus Ts, E minus temperature times entropy. And here the temperature, apart from a Boltzmann constant, is our smearing energy. And so now what we are really minimizing, obtaining, and computing is not anymore the total energy at 0 Kelvin of our system, but it's the free energy of this strange system with a fictitious temperature. And it's important to understand how big this term is, because if this term is very big, we are simulating a different system. Okay. And as I mentioned, in any case, this is not magic. I mean, still you need tricks to make it converge. And the common trick you have in all simulations, at least in most codes, there are more advanced ones, is to use a mixing parameter. What does it mean? It means that I'm doing a self-consistent iteration. No? So let me just go back to this slide. I do this calculation. I start with some charge density. I do my steps, and I get a new charge density. Naive thing to do would be I take the new one, I use it, and I start over. This is typically very unstable. What I want to do instead, I take the new charge density, and I only consider maybe 10% of the new charge density times 90% of the old one. So if I'm going the right direction, I'm minimizing a function, I just move slowly to the minimum. But I avoid that I start jumping between two solutions. It's a numerical trick. You have a parameter between 0 and 1. Typically, you would use a number between 0.2 and 0.5. You don't want it to be too small, because if it's very small, you move only 1% in the right direction. It did 100 steps to go to the minimum or more. So you want to, essentially, you want to have this number as large as possible. But if it's too large, you start jumping back and forth. And if you make it small, instead, you go down to the minimum. And so this is what, for instance, in quantum espresso, this is called mixing beta, for instance. It's an input parameter. It's a good default, but you often, if it doesn't converge, your calculation doesn't converge, the first thing you want to do is to adapt this number and reduce it. So let me try to give you an analogy in 2 dimensions of this issue of smearing and what it means. What we are doing is not very different from computing the area of a circle, but just putting points in a grid, okay, and computing how many points are inside, which would mean essentially taking a little square around every point, okay, and telling this blue area is my approximation of my circle area. The more points I put, of course, as you can imagine, the better my approximation is. If I have millions of points, I get a very good value of pi, which is the area of my circle of radius 1. However, you see already here from this plot as a function of the number of points. Here's 40 by 40, here's 10 by 10, here's 40 by 40. The value that you get with respect to the converged value of pi, which I know, and they put here as a red line, oscillates a lot. Okay, I need really to go above 100 by 100 to start getting numbers which are kind of close to the correct value, but still oscillating. And they oscillate a lot. They can even be larger or smaller, okay? And that's an important comment. If you remember, Nicola mentioned that Kohn-Sham equations are solving a variational principle. So you are trying to get the lowest energy solution in a space of functions. While for the basis set size, if you increase the basis set size, you have a larger space. So typically convergence of energy, for instance, as a function of size of the basis set will be monotonically decreasing because the larger, so if you take a small cutoff, you have some approximation. You take a larger cutoff, you have more options to improve your wave function. So you get a lower cutoff. Here, there is no variational principle for a discretization of an integral. So values can go up and down and you have no control. That's an important thing. And there is a lot of noise. Now you have very low precision. You would have to compute a lot of k points in order to get good results. Smearing means that instead of saying I only count points inside my circle, now I count 1 point inside, 0 point outside, but points near to the edge, I put a non-zero weight depending on how far I am from the circle. And you see here that now I'm putting some smearing. Here the color represents how much value I'm putting. Quickly, this value converges and becomes quite stable, but at the wrong value now. You see, now the value converges, but not anymore at pi, but at 3.17 maybe. Because I'm putting a systematic error because of this entropic contribution I was telling you. I'm not computing anymore the area of the circle, but the area of something different. And so if I do this, I need to find a balance between very low smearing, a lot of noise, but in principle, correct result. Large smearing, no noise. I can use a few k points. Now I can stop here, but the value is off. And I need to decide what value to pick, right? So should I use a small smearing and a lot of k points, but then my calculation becomes very expensive and possibly also very noisy. So I'm not even sure if I converge. Or I use a very large smearing, very small k point, everything converges, no problem, but then the value is not necessarily correct. Well, the good thing is that you cannot only use a Fermi-Dirac smearing, which is what you would intuitively use for Fermi-Dirac statistics, or Gaussian smearing. So essentially the integral of a Gaussian is something which also has the shape of a Fermi-Dirac approximately. But actually you can use advanced approaches, different functions, and essentially have a slightly different shape, but have a very nice property. And that's one, for instance, the one we recommend and we will always use in the tutorials, which is called cold smearing. Cold because it's like putting a little temperature, small temperature, right? It's been developed by Marzari and Vanderbilt, which essentially correct the behavior. So you see, this is the total energy, what you really want to compute is a function of smearing or broadening. And what you're actually computing is E minus Ts. You have a kind of parabolic, first order parabolic contribution as a function of T or smearing, which is wrong. And you don't want to have. There are approaches, for instance, for Gaussian smearing to say, okay, one is a parabola going up, one is a parabola going down, and you can prove if you sum them, you do the average, so you do E minus Ts halves, you can look at this reference. This removes the parabolic contribution. This gives you kind of constant, approximately constant behavior. So if you go to a large broadening, you still don't make a big mistake, big error. However, it's much better to use an approach like called smearing, which by using a slightly different shape has a similar behavior. I explain you why in words, and I show you the example of the circle that actually works. So the idea here is that essentially you have an occupation function, which is also 0 and goes to 1, but somehow has a little bump here above 1, okay? If you do this correctly, you can mathematically prove, and you can choose the parameters, essentially the square root of 2, etc., that removes the second order contribution, and you get a curve which is essentially much flatter. Let's see what it means in the case of our circle. If I now, this is my Fermi-Dirac smearing, okay? I go from a smearing in these arbitrary units of 0.01, 0.03, 0.08. You see that essentially I get better and better in terms of flatness, but my value goes off. Now, my value which I'm converging is not a red line. With the cold smearing, I can increase my smearing, and even with relatively large numbers, large smearings, I start getting convergence, but the value is correct. I'm going very, very little away from the solution. And you can see this even better here. So here I'm fixing the k-point grid. in my example, again, it's a toy example, 50 by 50 grid in my square. I'm trying to compute the area of the circle. And this is the area I compute as a function of smearing when I put Fermi-Dirac smearing. And this is the area I compute when I put cold smearing. Okay. And these errors, I computed by checking the error. If I do a 50 by 50 grid, what is the value I get if I do a 49 by 49, 48 by 48? I check 5 points close by. If I converge, I expect that it change by 1, the grid doesn't matter. If I'm very small smearing, value changes a lot. So you see, in both cases, we have very, very small smearings with this specific grid, I have noise, okay? I have errors. But when I go up in smearing, here, in order to get no error, I need to go here, but I start paying an error. For cold smearing, I have a large area in which my value is essentially correct, and I don't pay anymore this sampling error of the k-points. And by the way, note here the scale. Here is 3.14, 3.17. Here the scale is 10 times smaller. So this is really, really flat, okay? On this scale, this curve will be up here. Okay, so cold smearing is extremely effective, and that's why we suggest to use it, because you can now use reasonable k-point grids, so do calculation in minutes or hours instead of days or weeks, without having major errors in your total energy. These numbers were from a toy example, from a circle. No? I understand it's a circle, I know the area. If you do this for actual materials and you compute forces, you get similar curves, okay? You get, these are curves as a function of smearing of the force on an atom, for instance, on an aluminum system. As a function of the grid, you see, if we go from relatively loose grids to very large grids. And if you use few grids, the value is not correct, but when you converge, all these values behave quite well in this region of smearing. If you go to very small smearing, you start getting noise again. So you have a kind of nice sweet spot where you know which smearing to use and which corresponding k-points to use. So which values you have to use? You say, okay, now I don't know. What should I choose? Well, the good thing is in the years, we've collected a lot of experience on this. And we were hoping the paper to be out today, but it will be out tonight. So tomorrow you can find it on the archive. And I will tell you maybe again on Wednesday. We have did a work with Nicola Marzari, Gabriel, De Miranda Nascimento, and a few more co-authors to really do a systematic test on a few hundred materials to test what the contribution of these two errors are and get a kind of a way, given some threshold that you can decide on energy and forces, what the correct values of smearing and meshes you should use in order to have the energies and the forces below a certain error. So if you don't need anymore essentially to compute, to do this smearing, this test of convergence as a function of smearing and k-points, because you can just use the results you already have. And these are automated. So what you will see later in the demonstration, you just have to say, I want a kind of loose parameter. Essentially, you have three. Let me see if it's okay. It's not in the next slide, but you will see later. You just define 3 levels of precision. So which essentially determine how tight the threshold you want to be. You want a very fast calculation with acceptable thresholds, but just you want to see the results. You want something intermediate, balanced, that you typically want to run, or something extremely accurate and stringent. This determines the thresholds. And once you have the thresholds, we tell you which values of k-point meshes and smearing you want to use. Questions for this part? I don't know if there are questions in the Q&A. No. For people online, just type questions in the Q&A. We will try to answer. We won't be able to answer live, unfortunately. Okay. So last couple of points I wanted to mention before we go into the actual funny part, which is the demo, is pseudopotentials. And as I mentioned, these become essential if you want to use a plane wave basis set. Let's see why. Let's consider a simple atom, aluminum. Okay, aluminum has a 1s level, which is 1.5 kilo electron volt down. So for those of you here at PSI who do core level spectroscopy, you kind of know this energy is X-rays. Then you have a 2s, 2p, still a few tens to hundreds of electron volt, and only 3s and 3p, which only have essentially 3 electrons here, are of the order 1 to 10 electron volts from the Fermi level, or in this case, from the vacuum level. When you do chemical reactions, now typically you only interact with electrons here. unless you send X-rays, you never interact with these very tight 1s electrons, which are very close to the nucleus and very close, really very well bounded to the nucleus. So you really like to have a way to avoid computing these electrons explicitly, but to compute only the relevant valence electrons explicitly. So one, because they're only the one which play a role in chemical reactions, so bonding and making solids. The second one is that because of this, if you do 1% error of this number, you do an error of 10 electron volts, right? So it's a large error. If you really care about the energy difference, so imagine you want to compute the energy difference between an FCC and the BCC phase of a metal, and you want to know which one is lower energy. Now you want to do a phase diagram. These energy differences per atom can be of the order of milli-electron volt per atom. If you consider all these electrons, you have to be very, very converged, because even a 1 per mil error is still 1 electron volt error. If you can avoid computing this explicitly, you remove this, and a 1% error, 1 per mil error now becomes a milli-electron volt error, you're happy. So that's an important thing. You want really to avoid it. And the other point is these states are very localized, okay? And I can show you here. Not only these are very localized, but also these states have high oscillations because we decided to use a orthonormal basis set. So the 3s here has to be orthogonal to the 2s and the 1s. So if the 1s has a peak here, you see this very, very sharp. The 2s has to have an oscillation here in order to be orthogonal. So when you do a multiplication, the integral is 0. And the 3s has to be orthogonal to both. So not only you want to consider only this, but you really want to avoid to have these high frequency oscillations, because I need now to consider, if you want, a lot of points, a lot of grid points here, and a lot of frequencies in order to represent this function correctly. If I had only this smooth part, I would only need maybe, visually here, maybe 10 points, I can get a good representation of this part. But here I really need a very dense grid because I have these high oscillations. So how do I solve this? With pseudopotentials. The idea is, indeed, as you can imagine, I only consider a pseudo aluminum atom. Okay, so I consider a different potential, not anymore the 1 or the 13 over R potential of the nucleus of aluminum. I consider a potential which only hosts 3 electrons, 3 in this case, because I know these are not relevant. And I want that the 1s, the first solution of this, the second solution, 2p of this problem, have the very same energy of my aluminum problem. If I manage to do this, I will have a different pseudo potential whose ground state is not anymore the 1s, but is this new 1s, which has the same energy of 3s. I get a problem where this is 1s, has no nodes, so it will be relatively smooth. Second, I only consider 3 electrons instead of 13. So I have all these advantages I was mentioning before. And so what I will solve, so when I write my Hamiltonian, I don't write anymore my real potential 13 over R, but I write a different potential, which I'm going to show in a moment how it looks like. And I solve for different things, which are pseudo wave functions. With the advantage that instead of using a cutoff, now I say some numbers of 60 Rydbergs, which is something manageable. Here I can do 60 Rydbergs. Here I would have to use maybe 1,000 Rydbergs, which is orders of magnitude more expensive. Maybe you cannot even manage to put it in the memory. So that's the idea, okay? That's just what we want to do. But how we define a potential such that the wave function has these properties and behaves well? Well, the first type, if you want, of pseudopotentials are what are called norm-conserving pseudopotentials. And we show advanced methods just in a slide in a moment. But essentially, you want to put some conditions, okay? The first condition you want to have is that, as I said before, the energies of the states you're considering, the valence states here, okay, these energies are the same. It's intuitive, right? You want to still have the correct energies of the element, the orbitals. Then, again, if you look at this plot, you want to be away from the core. Okay, 0 here is the position of the nucleus. Okay, and these are the radial coordinates going away from the nucleus. You want it away. Sorry. Yeah, sorry. This is R. Okay, this is the distance from the nucleus. Okay. In this case, I think I don't even know if I put real units. It could be angstrom or Bohr. I mean, these numbers exactly, I don't know. I put just as an example. I can show you realistic ones. But you know that your nucleus, this is a solution of a Schrödinger equation of an atom. So you can put, depending on what you put for Z, if you do aluminum, if you do lead, you have the higher the R, the sharper this is. So at this point, I would just want to have an illustrative figure of how this looks like. Okay. But this is the distance from the nucleus. This is the wave function, the radial part of the wave function of your electron. And so 0 is the position of the nucleus. Now you want that beyond a certain radius, which you have to define, is going to be a parameter, the wave function is the same. They're on top of each other. Because again, you want to represent what happens inside the nucleus, you want to approximate that, and want to have something smooth. But outside, you want the behavior to be the same. So intuitively you say, beyond a certain distance, I define this parameter beyond the wave function are the same, the pseudo wave function and the real one. And then somehow you want this norm conserving condition, which is also the pseudo wave function should be normalized. Okay, which is to say that essentially the integral of the part within the radius is the same. So you still want something which has a norm 1. And then there are additional advanced properties that help with the transferability. Help at this pseudopotential doesn't work only for a single atom in vacuum, it works in different chemical environments. Let me first show you how it works. So actually you can, if you want to try yourself, there is a notebook online, which I prepared for my classes, so it's really interactive. You can click, you cannot click, you go on this URL, but I will show you a video, so you can do it later, you will have the slides. You can go in this section and you can try. And this is a very simple method to construct pseudopotentials, just the simplest which works because it's nice for illustrative purposes. There are more advanced ones and code generated. But essentially, let's say here, I want to consider a n equal to 3 state. So you see the real solution is the red one, has 2 nodes. For the channel L equal to 0, so an S orbital, I want to get a 3S, and I want to replace it with something which looks like an S. So what I do, the only parameter I have in this specific method is the cutoff, so which is a parameter I can move. And beyond, you see the blue and the red curve are on top of each other. Before, the method with the condition which I told you I will repeat them again, solves these equations and finds a different solution, which now is very smooth. So you can imagine that now I can sample space here with a very kind of coarse grid, just maybe 20 points here, and I get a very nice representation of this blue curve. And that's enough. Well, if I were to represent the red curve, I would need to have maybe 100 points, because here I need probably 3 or 4, at least 5, 10 points here in this region to represent it correctly. So again, to repeat, the red one is the Schrödinger solution of the 3S in the system. The blue solution is my pseudo wave function, and they can obtain what my pseudo potential is. Okay, so in this case, the red is the correct potential of a nucleus minus Z over R, diverges. In order to get this being the ground state, the code tells me this should be the potential I need to put. Okay, if I put this potential, I solve the solutions, I get the first ground state being this, where beyond this radius, the functions are the same, the solution is normalized, and there are a few more conditions in the specific method, which is you want the wave function to be continuous, its first derivative to be continuous here, and its second derivative to be continuous here. You put some kind of nice continuity conditions. If you go online, you can play with these parameters, and you can discover, for instance, that if you change RC and you compute it again, I make it smaller, you see that the shape now changes. So here, this before was going down here, now it goes up, and the shape is a bit different. You can play a bit with this parameter to then try in different environments, aluminum in an oxide, etc., which one is more representative. This is just, again, don't worry because you won't have to create pseudopotentials, but it's important to understand how it works. And the most important thing I want you to remember is that now the behavior depends on the angular channel. So the potential, if you don't have pseudopotentials, the potential is Z over R, 13 over R, whatever electron you have, whatever its angular momentum. When you start using norm concerning pseudopotentials, you have a non-local or semi-local potential, because the effect of the potential depends if you have an S-like wave function, a P-like, a D-like, etc. So you have to decompose your wave function into their angular channels and apply a different potential for each of them. Couple final slides about pseudopotentials and cutoffs. And this is important because you need to understand this concept. You will hear these words, etc. So the first thing you already saw before, we define a cutoff. I go back to the concept of a cutoff. I want to know how many plane waves I want to put. I define a sphere, and that defines my cutoff. Okay. Now, this is the way. This cutoff is to represent the wave function psi. When I now compute the charge density is the sum of square modules of psi, which is the same as the square of the periodic part, because psi and u just have a phase factor, which is norm 1. Okay, so, and this is the part which I represent with plane waves, u. U is written as a sum of plane waves with some coefficient. When I do a square modulus, I have to sum all possible pairs of square waves, of plane waves, because I'm just doing u times u, right? And so I get an expansion again in plane waves. If I multiply two plane waves, I get another plane wave with a different oscillation. But now, if I stopped before to a radius r, let's say, when I do the square modulus, I can get non-zero frequencies up to twice the radius. Because if I get this vector and this vector, the sum is here. But if I get this g vector, and again this g vector, the sum is out here, right? And taking two vectors inside a sphere, any two vectors, their sum can be up to a vector which is twice, within a sphere, twice the radius. And since I don't want to measure the radius, but I want to measure the cutoff, which is squared, right? If I have square radius, it means I can go up to 4 times the cutoff. So that's important. So if I want to have a cutoff in my code to a maximum energy of my plane waves to represent correctly my wave functions, let's say 30 Rydbergs, and I use a non-conserving pseudopotential, I want to represent my charge density with a more dense grid somehow, with more plane waves, and I don't want to put this number random. I want the ratio of the two cutoff to be exactly 4. So if I give you a non-conserving pseudopotential and they tell you should use 30 Rydbergs for the cutoff on the wave functions psi, you want to use for sure 120, 4 times more Rydbergs for the cutoff on the charge density. There might be cases in which you can go down a bit because you're kind of very converged, but in general, this makes your calculation fully consistent. Now, people said, okay, especially even now, but especially when calculation was very expensive, can we make it even better? Can we make even better pseudopotentials? And Vanderbilt came out with this idea of ultra soft pseudopotentials, and they are used. So at least if you know that you see the name, you know why, what it is. Well, essentially, this is specifically important when you, for instance, you have a 2p of oxygen. No? 2p has no nodes. It's the first p orbital, right? So you cannot do much better. If you try to do a pseudopotential, you do. Now you still use pseudopotential. You know, the pseudopotential and the real wave function, so the pseudo wave function and the real wave function essentially are the same. So you would use the same cutoff. That you cannot change it. Well, the idea of Vanderbilt is that we do something called ultra soft, where essentially we split the wave function in 2 parts. The ultra soft wave function, which is smoother, plus a core augmentation charge. Now, these objects are not normalized anymore, are only normalized in a general sense. You have to consider this augmentation charge. But the advantage you get, so the math and implementation is more complex. That's why sometimes you might see codes not supporting ultra soft pseudopotentials, because they have to write the algorithms in a much more complex way. You have to consider now your wave functions are not normalized anymore. But the advantage is instead of having a very peaked wave function, you have a smooth wave function. So you can go down in cutoff. Now, going down in cutoff, as my comment here, now the charge density is physical, something you could measure. So that's the cutoff is what it is. But thanks to this, you can go down in cutoff for the wave function. So before I said 30 and 120, or maybe this is kind of small cutoff, let's say 60 and 240. Now maybe you can go down to 30 and 240.
So you can use a smaller cutoff for the wave functions, which is the most expensive part of the calculation. You have to do all these Fourier transforms to go compute kinetic term and potential term. And therefore, the ratio now between the cutoff for the wave function and the cutoff for the charge density is not going to be anymore 4, but you can be 6, 8, 12. Okay, you can get even cheaper calculations. Now, after all this, you say, okay, what should I do? I have no idea what is a pseudopotential, what cutoff I should use. Again, luckily, in the past years, we've been working a lot, and we have a curated library of pseudopotentials called SSSP, which is online, which not only tells you, gives you, so we went online and we curated about 10 families of pseudopotentials for the periodic table. Not only we tested them, we see which one are working fine and correctly, etc., produce correct results, etc., but also we tell you what is the cutoff you should use for that specific pseudopotential. So if you want to do a calculation, you can go here, take the pseudo, look at the cutoff we suggest, and run it. You don't have to. For typical calculations, this will be converged. Okay. And here again, we have two families, an efficiency one and a precision one. Precision is more precise with respect to the correct DFT result, sometimes requiring much higher cutoffs. So for typical calculation, the efficiency is enough unless you have a very specific system you want to compute, and then we recommend using the precision one. And by the way, just to mention a work we did last year, we are continuing to improve the pseudopotential quality. We had done a work with involving about 45 authors, when there are codes which I didn't discuss here, not like quantum espresso, which is plane wave pseudopotential, but they are all electron codes with different basis sets. But they also are more expensive, but they can also compute these quantities in DFT in a very accurate way. And so with two codes, Fleur and Vin2K, we computed for the whole periodic table and for every element for 10 systems, cubic, simple cubic, FCC, some oxides. We computed the equation of states, so energy versus volume. And we got a very nice reference data set of 960 equation of state for the whole periodic table. With those, we can now test if our pseudopotentials reproduce correctly or not the equation of state. So elements in different chemistry, oxides, unaries, at different volumes, and we try to see if they work or not. And this, we could then compare the results with several codes, not really codes, really. When I say code, is really code plus which basis set plus which pseudopotential they used. And for instance, quantum espresso with SSSP is down here, which is, together with other plane wave codes, quite precise. And we are still doing work to improve it. And this is kind of the error on the question, on the parameters of the equation of state. You see already that the advantage of plane waves, they're more expensive than localized basis sets, but the codes use plane waves are typically those which are very precise results. Because you can just increase the basis set, that's the only parameter you have to do, and then improve the pseudopotential. The codes which have a slightly larger error are typically codes which use a localized basis set, which is not systematically improvable. This work wasn't done to improve the basis set, so they did the best they could. But you see that they couldn't do better in the 2 years in which they did the work, because it would require for every element to improve the basis set. For plane waves, you just increase the cutoff until it's converged. It's expensive, but you can test the pseudopotential. Okay, I want to give a few more quick comments you will see in practice about how to run our magnetic systems and system with spin orbit. It's really 3 slides just to get a sense of what it means, and you will see them in practice. So if something is unclear, maybe we can also ask after the demo. Before I go on, questions on the pseudopotentials? No? Okay. So let's go forward. Magnetic systems, here I explain specifically in the case of quantum espresso, but the idea is similar for all codes. First, so up to now, I've been discussing systems which are essentially non-magnetic. Every state is occupied by spins, so spin up and spin down. There is no magnetization. If I want to study collinear magnetization, so I fix a quantization axis, and I can only have a spin up and spin down with some amplitude, I don't have an angle, then in the code, I say I want n spin equal to 2, which means I want to consider 2 spins. Essentially, what the code does is to have 2 sets of k points, the k points for spin up and the k points for spin down, and solves the equations independently. The charge density is the sum of the contribution for spin up or spin down. In the output, you see essentially, if you want twice as many k points, in a sense, it's the same number of k points for spin up and spin down, and twice as many bands. And now bands are occupied only by 1 electron, because you have the bands for spin up and the bands for spin down, which don't mix. If you want to do non-collinear magnetization, so you have, we want to simulate spin spirals, so anyway, you want to give any angle to the spin, then you have to use non-collinear magnetization, which is in the code is n spin equal to 4, and you activate with this flag. Doesn't matter, we see. You don't have to set it to my hand. And the idea is that now you have, spinors to solve. Now you have to solve direct equation. So the equation become a bit more complex. You have two component spinors, and that's why the code requires different treats the code the equation in a different way. And now again, now we can have coupling. Now you get the same number of K points, but you get again twice as many bands. However, now, especially if you do spin orbit, okay, well, I'll go to spin orbit first, maybe. You need to have non-collinear treatment, and you have to turn on spin orbit treatment. So you have to tell, please also add the spin orbit coupling terms in the Hamiltonian. To do this, you need fully relativistic pseudopotential. So the pseudopotential itself needs to know about spin orbit, essentially. And in SSSP, we don't have them, but there is another very nice library online, the Pseudodojo. If you go on the website and you select the type, you have to select the FR, which stands for fully relativistic, which means they include the contribution for spin orbit. Otherwise, the code will not do anything, essentially. Just don't put any splitting. So for spin orbit, you have to do both. You have to use non-colline equal to true, because you have to allow any direction. You have coupling, so you don't have any more spin up and spin down bands. No, you have a mixture. And you have to turn spin orbit using the correct pseudopotentials. Going back for a moment, so forget for a moment now about spin orbit. You want to do iron. You want to do ferromagnetic iron. What do we do? Well, it's relatively easy. You define the input in a way which doesn't matter because you will not have to write it in a sense, but you write, I want iron in the origin in a given lattice, BCC, and then I say I want a starting magnetization of 0.1. You have to tell the code, please, I think this element will have some magnetization. I put it away from 0. So during the self-consistent relaxation, the self-consistent cycle, the code will try to find the correct magnetization. So if you put it 0, because of symmetry, so if you go to plus or minus, it's just a number along the quantization axis. So plus or minus just means if it's up or down. At 0, there's a perfect symmetry, and the code doesn't know if it should go left or right, and it remains non-magnetic. So you always have to put some non-magnetic, non-zero value. So ferromagnetic, it's easy. What about anti-ferromagnetic? Well, if your cell is big enough, you have enough atoms, you just put positive and negative starting magnetization on the corresponding atoms. If you have a very small unit cell, you have to make a bigger cell. So if you have iron BCC and you want to do anti-ferromagnetic, you have to at least double the cell, have 2 iron atoms, and at that point, you can put 1 up and 1 down, and the code will try to give you an anti-ferromagnetic solution. This is something you will see, not with the input, but with the GUI in half an hour. So summarizing, you can do collinear magnetization, you can do non-collinear magnetization, which is also required when you do spin orbit. If you want to do antiferromagnetic, you might have to increase the supercell size to have enough atoms, and of course, it depends also which kind of antiferromagnetic order you have, if it's planar or some other order. One technical note that's important, units. So every code uses different units, luckily, or unluckily. VASP, for instance, is using electron volts. Many other codes use atomic units just because the equations are much easier to write. You don't have to put SI units. You just put 1/2 or 1 for the nabla, for the kinetic term. There are 2 atomic units, again, unluckily. There are Rydberg atomic units and Hartree atomic units by a factor of 2. Okay, 1 Rydberg is 13.6 electron volts. Hartree is twice as much, 27.2. In quantum espresso, units are Rydberg. So when you put an it's in the documentation, but if you put a number, it's typically Rydbergs, and the output will be in Rydbergs. In other codes like Abinit, which are also the code, main code behind the Pseudodojo, but this also works with quantum espresso, they use Hartree. So there's a factor of 2. So when they recommend a cutoff of 30, Hartree, in quantum espresso, you have to put 60 Rydbergs. That's important to avoid mistakes. Okay, they give you a converged value. You have to make sure which units they're using and which units you are using in your code. Again, luckily, we'll do it for you. But if you want to download it for you and do it your calculation, be careful about the units because this can make a very simple mistake. Okay. Summarizing what we learned until now. When you want to run, the most important thing you have to do is to put the crystal structure. You have to define a lattice and put the atomic position in it. You have to choose which basis set you want to use. In quantum espresso, you don't choose a type, it's always plane wave. But you have to choose how many plane waves you want to put. You choose the cutoff for the wave functions and the cutoff for the charge density, whose ratio is typically between 4 and 12, depending a bit on the type of pseudopotential. You have to compute integrals in the Brillouin zone. So you have to compute k-point sampling, and you have to put a grid. If it's a metal, you also need to put on smearing. You want essentially always use cold smearing, and you have to decide the magnitude of the smearing. If you're a magnetic system, you have to put some initial magnetization on some atoms. And if it's anti-ferromagnetic, you have to start with an anti-ferromagnetic configuration. And then you have to set up some numerical parameters. As I said, there is a mixing, for instance. So if it doesn't converge, you have to change the mixing. There are some other parameters in the input. Then you run it and fingers crossed, you hope it converges. And you have enough CPU to run it. But there is a lot of things now. I just told you what are the things to set up. I didn't necessarily tell you which values to put. And as I told you, there are a number of tools we've been developing, and we collected them in what we call the quantum espresso input generator on the Materials Cloud. Again, a link which will be very useful. You will find it again in the slides when I upload them. How does it work? You have a very simple GUI again. You can upload a file, your input file, your crystal structure. You just can select a few parameters. You select which functional you want to use. You remember PBE, PB-SOL. The level DFT. You select the protocol if you want a fast protocol just to test but it will not be converged, a balanced protocol which is typically enough, or a stringent protocol which is typically very accurate but also very expensive. And then you decide if you want a system to be magnetic or non-magnetic, and if you know it's not a metal, it's an insulator, you tell it because it's going to be cheaper. You don't have to put smearing. And the tool will just immediately show you the input file of Quantum Espresso using all the values we recommend. And you can download it. You download also the SSSP Pseudopotentials. So essentially you have a folder which you can just put in a supercomputer and run. You can just use it to run, or if you prepare your input, you can compare to see if your parameters are what you expect or not. It's an interesting exercise to see if you're converged or not. Or what we see in 5 minutes, you use the Quantum Espresso app, which uses the same logic, but also runs it for you and shows it in a GUI. You don't have to look at the text input file, look at the text output file, copy files, but runs it for you in a GUI, shows the results. We can also run more advanced workflows that we see on Wednesday for muons, XPS, phonons, etc. And also has workflows around it to improve the robustness. For instance, if you're typically, when you run on a supercomputer, you run for a given number of hours, and then they stop you, 12 hours, 24 hours. If the calculation goes past the 24 hours, our workflows in AiiDA, which is our workflow engine, will detect it, stop nicely the calculation, and restart it. Or if something doesn't converge, it will try to reduce this mixing beta for you, for instance, or change some minimization or diagonalization algorithm for you if it thinks a slower but more robust one could work. So it's not only does some automation for you, but also improves a bit the robustness. We have to think less about the technicalities. And if you want to know more, there are a lot of online materials. I suggest to go on the Materials Cloud Learn. There are a lot of schools we did, or other people did in the past, which are there with videos and tutorial, or with this video, of course, recorded. And with this, we finished the theoretical part, and we go now into the more practical part. So again, questions? Yeah. Yeah, so it's 4 because you have 2 spinors, essentially. So essentially you have a spinor wave function, and again, you have 2 spins. So this turns out to be 4. It's a numerical way in which the code is implemented, because essentially at every wave function, for every n and k, will have 4 numbers. That's what it does internally. So it has vectors of 4. And the point is that you have, if you write the Dirac equation and you solve for the matter, not antimatter, you get spinors, which have 2 components. And then you want to have a spin up and spin down, essentially. Bands. Okay, that's a bit in words the idea of Y4. Then in the end, you will have a vector that you can project on X, Y, Z, and you get a spin on the components of the spin.
But this code just cannot find the ground state of of certain anti-ferromagnets, certain orientation. We explicitly set it, and then things that it is beyond the orientation space.
So the code solves this, tries to minimize the energy using a self-consistent approach, and it's a local minimization approach. So when you start doing anti-ferromagnetic system with non-collinear spin, the energy landscape is not very smooth, it's very complicated. There are a lot of small minima, a very small different energy difference between them. If you don't start very close to the minimum, so you don't already know more or less what you want to do, and even in those cases, not easy if you have a lot of different complex configurations, the code might not converge, or might converge to a local minimum, which is not necessarily the ground state. Maybe a antiferromagnetic with different starting spin, with different spin configuration, etc. There is work, I can give you references later, where colleagues in the laboratory here and in the EPFL with Nicola Marzari have been working in automating the search. So you try to search with some constraints a lot of different magnetic configurations, you compute the energy, and you find the real ground state. This is very expensive, so we do it typically in high throughput searches. We first go down to a few candidates, and when we get 5 to 10, we use this method. Because for every system, if you really want to do it, you have to do, maybe 500 different calculations, to discover which one is the ground state. Moreover, we are in periodic boundary conditions. So if you have spiral states, for instance, you have to have a commensurate unit cell. Okay, so that's another point. So the code in principle will find it, just that it's not necessarily easy to know how to tell the code to start correctly, So for very complex magnetic systems, it is a tricky problem. Yes. So there are ways where you get Hamiltonian parameters in a unit cell, essentially the coefficients, the magnetic coefficients, and then you use other codes in a larger supercell to find the spirals. So you wouldn't necessarily do a supercell in the code. You can have other approaches. But yeah, otherwise you have to use a commensurate cell in quantum espresso if you really want to see a state which is a spiral. Yeah.
Would a superpotential for let's say a positive valence atom is different to that of a neutral atom? For example, iron and iron 2+, for example, would superpotential be different?
It depends. So it depends on the transferability. That's yet another level of transferability. Typically, one tries to have a pseudopotential and test it. So kind of in the atomic configuration, you move a fraction of an electron in some higher energy in order to make sure you simulate with the same pseudopotential different states, oxidation states. Because otherwise, in a system, you have a battery, cathode, and you cannot decide which one. You want the system to tell you what the oxidation state is. There are special cases in which you can do tricks. You want to force some oxidation state, but typically the idea is that you get a good pseudo, which also works for maybe, I don't know, 2+, 3+. Okay. So we run directly into the practical part. So the hands-on session. So let me just first 5 minutes tell you what we're going to do, and then you're going to start up your laptop and try. So first of all, we are going to present you tools that partly we develop and partly are open source and exist and are developed not necessarily by us, but we have a full stack of open source software. So all what we do, there is no commercial software involved. At the lowest level, there is a Quantum Espresso, which is the actual DFT code, which I mentioned several times. That's something that not myself necessarily, but other people in the laboratory here develop, and also in other places, but it's a code that you can find and download. On top of it, we run the workflows with AiiDA. AiiDA is a workflow engine that we develop here mostly at PSI in collaboration with some other places in Empire around the world. And this is really the workflow engine that takes care of running the simulation for you, to connect to the supercomputer, copy the files, wait till they finish, parse the results, check if there is an error, try to fix it, etc. So there is AiiDA itself, which is a workflow engine. There is an AiiDA Quantum Espresso plugin, which knows exactly about Quantum Espresso, but AiiDA is much more general. There are 150 plugins nowadays, also beyond DFT, also for atmospheric simulations, weather and climate, and so on. Also, AiiDA is very much focused on provenance, so keeping track of exactly what you did. So you can easily download it. I will show you later, and if I forget to show you, remind me, or you remind me, how you can easily get all the calculations that were run in a GUI in a way that you can just upload it, and if you publish a paper, you can get the files and put them in an archive in 2 clicks. But AiiDA is still a Python tool that you have to use Python and a Jupyter notebook, and you have to write code, which is convenient if you want to do things automated, like if you want to run high throughput, you want to write scripts. But if you want to run a few calculations, it's easier to have a GUI. Therefore, in the past 5-6 years, we've been working on a GUI called AiiDAlab. And again, AiiDAlab is general, is more like a GUI for AiiDA. And specifically, what we're going to present you is AiiDAlab Quantum Espresso. It's a specific app. So in AiiDAlab, you can have multiple apps, multiple applications. We will present you specifically the one for Quantum Espresso, which allows you to run basic calculations, relaxation, total energy, band structure. But we'll see in the past few years, us plus a number of colleagues around the world, in Bremen, in Italy, in Parma, in Modena, etc., in EMPA, etc., we've been developing a lot of workflows to facilitate advanced properties. And in fact, the next session on Wednesday is a simulation for large-scale facilities. We'll go not only in relaxing a structure, but properties you can actually measure. So that's the kind of stack. And before I forget, it's important to acknowledge all the people behind it, because it's a kind of Quantum Espresso. It's not even mentioned here. It's a 30+ year effort. But AiiDAlab Quantum Espresso, there's an effort of 10 years now with a lot of people involved. And you see here a number of people who have been involved in one of these components. And because otherwise you don't get the money, here is a slide with the funding of the institutions and projects which have been supporting it. And also I want to mention, so there is a number of like the people in Parma for the ones, the people in Modena for the XPS and XAS, a number of projects we got here in Switzerland, institution PSI, EPFL, EMPA. Marvel has been put a lot of funding and also Max behind all these tools. Marvel is an NCCR in Switzerland. Max is a European project. Bremen for all the developments on phonons. And I also mentioned Azure because for the next 3 days, for those of you who are here in the room, we give you access to a virtual machine, which is sponsored by Azure. Okay, now you can turn on your laptops, and there are different instructions if you are here and if you are online. So if you are here, you can log in this URL, okay, psi-tutorial.aiiDAlab.io. If you registered with your GitHub username, you will be allowed to enter. If you don't manage, it means you didn't give the correct username in the form. Don't worry, we can fix it later. Anyway, a comment for everybody, also those online. We'll now go through some examples. It will be just half an hour. It's more important that you watch. So if you realize you don't manage to log in, we are going kind of too fast, you miss a step, everything, you can watch the video again. Actually, you will see everything is explained in the app. We have tutorials in the app, so you can do it yourself. After this, in half an hour, we have a break. So for those online, you can write on Slack if you have issues, and we try to help it today and tomorrow. For those here, we have a coffee break, but we're still here until 5. So if you have questions, we can fix it now. So don't worry, but we will give you now 5 minutes to try to log in. So people here, you go to this URL, you find a page which looks like that. You log in with your GitHub account. For those online, you have received instructions by email. This is also valid, of course, for you here to run AiiDAlab in your laptop. Okay. For this tutorial is enough. Then we will show on Wednesday how you can connect to supercomputers. But for today, it's enough to run your laptop. There are multiple ways because it depends if you are on Windows, Mac, Linux, but they are all documented. In principle, you should already have installed it. You won't have the time to do it right now. If you did it, either you run this command if you use the AiiDAlab launch approach, or you go on Docker desktop and you start it. In both cases, your browser should open, or you should open your browser to a local host and a port, which might be this, might be 8889, depends how you configured it. Okay, so either you launch on your laptop, or you go to the URL, and you should get to a point where you see this window in your browser. Okay. Again, I'll give a minute. People can log in, get their password, etc. Then I will go on. If you don't manage, just turn off your laptop and watch here. You can try later. Okay, so just to get a sense, how many people see this? Few. I wait 30 more seconds and then we go ahead. Okay. There are questions in the meantime? GitHub.
You should have given the GitHub name before, otherwise that will not work. We only approve the access to you, essentially. Just to get a sense, maybe I go to the next slide, since we'll give some time. So running these VMs for hundreds of people, it's 1,000 francs per day. So, it starts to be expensive. I mean, probably cheaper than the coffee break, apparently, but still quite expensive. So we'll keep it alive for you for 3 days until the end of Wednesday, maybe Thursday morning, and we turn it off. The good thing is that you don't have to, so it doesn't mean you cannot do anything. First of all, you can run on your laptop. Second, so this is also to say that you should download your data if you did something, okay? Because we delete everything on Thursday morning. And also the Slack channel for support, we stop monitoring on Thursday. There are standard channels to get us support from AiiDAlab and AiiDA, so you should use those. Slack is really for these 3 days. There is a demo server, which maybe don't go now because we're going to update it in the next couple of days, but it's open to everybody in the world, but no storage. So you run for 12 hours, you see how it works, and it gets deleted. So just really to see how it works. And you can run your laptop. And for those of you here at PSI, we maintain a PSI instance, which works only inside the VPN, but then you don't need to have your laptop, and it's all pre-installed. And this being inside the VPN, you can also connect to the PSI supercomputers like Merlin 6, Merlin 7, and we maintain in our lab. By the way, for those of you who are at PSI, even those who are online but can come physically in PSI on the 29th, we will have a session for any of you who wants in OVGA in the other side on the east for 2 hours. We'll be there. So if any of you wants to ask us something doesn't work, etc., want to come in person, we have a 2-hour open office, let's say. Just take a note and we are there. Okay? Is there a date right? I think so, no? Okay, so I'll now start. So I need to manage to first stop sharing somehow. And let me share my desktop. And again, for people online, please use the Q&A if you have questions, because I won't have time to answer everything. Okay, we're kind of on time. When you're here, you have a few things. So you have a few general buttons. These are for AiiDAlab. You can, behind the hood here is Jupyter, okay? So you don't see it necessarily because we on purpose hide it, but in reality it's a standard Jupyter. So you have a standard Jupyter interface to upload files. You have some space to put files. You can open a terminal if you really want to. But we will focus on this app. You have a few things you can do. Let's start to run a new calculation, right? There are a few things we'll see later. There are some examples. You can discover what quantum espresso is. You can see the calculation you already run, but now you didn't run anything, so it doesn't make sense to go here. Let's click on new calculation, the first button. So you click on it, wait a few seconds, and you get a wizard interface, which helps you run your first simulation. At the top, you will see there are a few buttons, again, to go to different places. The important thing is that you have a tutorial, okay? It can be a bit slow because there are many things are starting, but let me just close other windows. Okay. When you're here, the nice thing is that we have written a number of tutorials. So if you click on tutorials here, you have a number of tutorials which we'll present in the next few days. What we will do today is to look at the relaxation and the electronic structure tutorial, basic tutorial. If you see, when you select it, a number of green text here appear. So before there was nothing. Now you get instructions, okay? So this means that you can do it yourself without my help. I will keep them on. I will not read them. It's just annoying for you if I keep reading. But I will tell you, so I will go faster. But again, if you get lost, you can go back to instructions. Okay, now activate the basic tutorial. What we will do is written here. We want to do the band structure of gold, the PDOS of gold, and the fat bands of gold. If you don't know what fat bands are, you will see in 30 seconds. Let's start with step 1. As we said, the first thing to do is to upload a structure. And there are many ways. You might have a zip file on your computer. You can click.
There is an Optimate database, which is a standard API to query different databases. There are Materials Project, Materials Cloud, Airflow. So if you have a structure there, you can query directly from here and import it. You might have already run it, so you can rerun something on a structure in your database. And in this case, you click on From Examples, because we're going to run one of the few examples we provide. We stay with the simple, so From Examples, simple crystals, and we select gold. If you have a visualizer, you can, it's a very simple system, right? It's a one atom in a unit cell. You can play with appearance. This is just the appearance. So if you make a supercell here, it's not going to run a supercell. It's just to visualize it. Okay, it's still going to run a one by one supercell, unit cell. So I don't put it. And you can look at properties of the cell, the lattice parameter, the volume, the angles, etc. Once you're happy and we don't do anything, we later will see how to edit the structure. We can also already here move atoms, make supercells. But let's say now we want to have the simplest tutorial possible. I want to run the primitive cell of gold. I confirm the structure. And I go to the second step. There are 4 steps in total. The second step, I have to decide what I want to do. The first thing I need to decide is, do I want to relax the position of the atoms in the cell or not? There are 3 options. You can run the structure as is. You don't want to move atoms. You don't want to change the cell. Or you might want to change the atom positions if they're not at the minimum position, but don't move the cell, fix the cell, because maybe you know it's a specific system with a specific C over A, you want to fix it. Or you want to let the DFT find the ground state configuration. We keep full geometry here. Let's say, I'm not sure if I put the right lattice parameter. I found it online. I have no idea. I want to get a DFT value, so I select full geometry. And now I go to select what I want to do. So I open 2.1. And here it starts to be interesting, because here I can select what I want to do. What we will do now is to tick the first 2 boxes: electronic band structure. We want to do a band structure, and electronic projected density of states. We want to do a density of states, a DOS, with projections to know what are D states, what are S states, and so on. So I select the first 2. I don't select for now the other ones. We will see later. What we already installed in this machine are plugins for Bader charge analysis that we see with Sheng on Wednesday, muon spectroscopy with Miki on Wednesday, and vibrational spectroscopy, phonons, that we see with Miki and with Andres also on Wednesday for inelastic neutron scattering and for infrared and Raman. So let's not select them, otherwise the calculation takes too long. In addition, there is a plugin store. You can add more plugins. Maybe if you have time, we'll show you today, but essentially there is a way to add more plugins which we already developed. And we will just mention some of them at the end of Wednesday. We have plugins for core level spectroscopy, XPS and XAS, Vanier function calculation, and properties on top of Vanier functions. Hubbard parameters, so DFT plus U. We'll hear about DFT plus U. You already heard the theory, and we see how to run it, how to put a U value in a moment with Timo. But these are fixed values. Say I want a 5 electron volt of U. Here you can compute a correct U, the self-consistent U, as Nicola mentioned. And there are a number of additional post-processing. For now, let's just pick band structure and PDOS, and we're going now to customize the parameters. The first thing is basic settings. Whatever I do, I want to select. If it's a metal or an insulator, if you're unsure, you choose metal. Gold is a metal, so you have to use metal. Otherwise, it will not converge for the reason I told you, which means use mirroring in them. So when I select metals, it means I'm telling the code, please use this mirroring. But if I know it's silicon and there is no gap, so there is a gap, it's not a metal, I should use insulator because the calculation is much faster and much more robust. Gold, non-magnetic, I don't want to put magnetization. I should put spin orbit because gold starts to be maybe heavy, but it's heavy, so we don't do it. We do no spin orbit. And important for this tutorial, I select fast. That's the important thing you have to do now. Otherwise, it will take just too long. It's going to be fast, so you get something which makes sense, but it's not for publication. When you do publication, you want to use at least balanced. But for today, please select fast. Otherwise, it will take more than 5 minutes and you don't see anything interesting. There are a number of advanced settings, which I'll skip completely because it's the focus of the next presentation by Timo. But I want you to go to the additional tabs. Since we selected that they wanted band structure and PDOS, new tabs appear for customizing parameters of those properties. In particular, for band structure, we want to select fat bands. This requires additional calculation, so it's not on by default. But you want to see it, it's nice to see, so please check it. For PDOS,
You can open it if you want. We select the default for now. We don't need to change it, but you can look at it later. Once you set fast in the basic settings and you set fat bands on in the band structure settings, you confirm. With this, we are done for the parameters. This is enough for our workflows and our GUIs to select everything: pseudopotentials, basis set, K-point meshes, etc. Everything is done thanks to what you just wrote here. The final thing to decide is where you want to run. You have to run somewhere. For this tutorial, we put Quantum Espresso on the virtual machine or on your laptop. So what you installed, if you installed on your laptop, contains also Quantum Espresso and a few more codes. Of course, this will work only for these tutorials because it's small. Okay, if you run a real simulation, you have to go to a supercomputer with more CPU. So tomorrow on Wednesday, Xing will tell you how to go to a different supercomputer. You can just set up new computer. You can say, I want to go to Merlin, my Quantum Espresso executable in this path. But for now, you don't have to change anything. I just tell you what it is here. You can select which code you use for every executable you have to run. When running this, you have to run multiple executables. PW is the Quantum Espresso executable to run charge density relaxation, the self-consistent cycle. But you need also additional code to do the projection, the PDOS, and the DOS. Here we only have one, the one we selected. When you install on Merlin, for instance, on your supercomputer, you have more in this dropdown, and you can select, and AiiDA will connect to those supercomputers for you. It's the same thing. And since it's just your laptop, just choose one CPU. It's enough for this tutorial. You can choose more nodes in the future. Once you are here, we are ready to submit. Before you click, if you click this, okay, don't worry, you can change the label and description. We already put a label which makes sense, but you can write more. Okay, you can say my first calculation, and you can write more text here if you want to remember something that you can query for later. Now we are ready. We click submit, and now everything happens behind the scenes. The workflow reads what you decide to do, prepares the input, connects to the supercomputer. In this case, it's still your computer, but in principle, it would SSH to Merlin to a different supercomputer, create the files there, submit to the job scheduler, and wait for the calculation to finish. While this happens, you can look at what's going on. So this tells us the workflow is running. If you made a mistake, you can kill it, stop it. I will not click it, otherwise we have to submit again. And here we start having a little overview of what's going on. And as I said, it's not just a single calculation. No, the nice thing of the Quantum Espresso app is that it takes care of automating a lot of steps that you would have to run by hand if you didn't have the GUI. For instance, here, what's happening is that I'm starting to run a structure geometry optimization. It's actually already finished in 20 seconds. But you will see it becomes red because we are running with very loose parameters. And even if the calculation finished, you see here, the workflow realized that probably is not really converged. I want to run another step. And if I clicked on the second step, you will see actually you can see live what's going on. When the calculation actually starts running, you see the code scrolling. So if you are curious to see what the calculation is doing, you can see happening here. If you ever use Quantum Espresso, you should recognize this output. For those, since we are waiting for a second, for the technical people, I told you before there are no Poulet terms in the forces because the base set doesn't depend on the position of the atoms, but it does depend on the cell. So when you relax the system, if the cell changes, the number of G vectors you have to consider is different. That's why the workflow is running a second relaxation to make sure it's really converged. This will run in a few steps. Maybe while it runs, I will show a few more things. First of all, you have a summary tab. You see basic properties of the label and description you chose. When you run it, you see the parameters you chose. And later we will go back here to download everything. So if you want to have on your computer the input files and the output files, you can go back here and you get them offline. And later we will go in this results tab where we can see the results for the structure and the electronic bands. For now, things are still running, so we don't see anything. As soon as they finish running, magically these buttons start working. So let's go back here. You see now things finished. This step, the relaxation, is complete. And actually, if you go here, you see now we're already in the results. We can start already seeing the difference between the initial structure I put in the input and the relaxed structure by clicking on this button. This is the relaxed and this is the initial. It's called single side. You don't see anything on the graph, but you can look here. Okay, the lattice parameter in the initial were 2.885. At the end is 2.878. So it did something, okay. And it's gold, of course, don't expect magic things happening, but the system relaxed the energy. I go back to the status, let's see. So this is still running my
band structure, okay, and my PDOS. So whenever one of the two is finished, here I will see some results. Since I have to wait a few seconds, it's taking a bit of time. Questions up to here, things which were unclear? Yeah. So many levels. At the moment, 0, in the sense that, or let's say 1, in the sense that we're running one CPU. So it's the code itself is not parallel. And in this demo machine, I think we're running 2 jobs. So we have to assume we have 2 CPUs and we run 2 things at a given time. All the rest gets queued. So in this workflow, things run maximum 1 or 2 at a time. In some cases, they have to because there is a dependency. First relax and then run the properties. In some cases, we see, especially in the phonons, in the muons, you have many supercells that you run in parallel. So if you run a supercomputer, all of them are submitted. And if you have enough CPU, they run at the same time. In addition, for every calculation, in the step 3, you selected how many nodes and how many CPU to use. So the code itself is MPI parallel. So you can run on multi-CPU and possibly multi-node. And you have to have a bit of sense of, if you put a large number, it's not necessarily going to be faster, but to a certain level, you have that level of parallelization, and you can set this level of parallelization per code. So for instance, for the PW, it makes sense to do it. For the DOS, it's very fast, a fraction of a second. You don't want necessarily to parallelize it. You can even run on a different computer. So the hub helps you doing certain things, and what is tricky, you need to have a sense of how to parallelize your code in a supercomputer. Okay, so this is, one part is already finished, the band structure, the PDOS. Okay, the PDOS also finished, so now everything is done. You go in the results, and here everything is finished. You click on load results. So I went results, electronic bands and PDOS, load results. And now you get a nice plot, okay? This is the band structure of gold. Here is the PDOS on the same energy axis. The colors are the different orbitals. And I just tell you how to use this plot if you never used the specific library. So you can drag to zoom, okay? And both are synchronized. You can double click multiple times to switch between different zooms. Essentially, there is a kind of default zoom, which is around the basic levels you care about. You can double click again or use the auto scale to really see everything, including some of the semi-core states. As I told you, the pseudopotential removes the core states, but some semi-core states might still be there in the pseudo to have a good pseudopotential. So this, for instance, we want to know what it is. Very easy, because we did run a PDOS. You see, this green is the 5S of gold. So you don't have 1S, 2S, 3S, 4S, 5S, but we have 5S. Some pseudos don't have it necessarily, but people who generate this pseudo decided it was important. It's flat because it's a core state, a semi-core, essentially almost a core state. So there is the energy to hop between 1 4S in one atom and 1 4S in the other atom is very high, because they're very localized. It's very hard to make a 5S move from one to the other. And the bandwidth, we didn't have time to discuss it, but the bandwidth is related to the hopping probability, the hopping energy. The flatter it is, the harder it is for the electron to hop. That's why the core states and the semi-core states are essentially flat. So I told you about zooming. You can even change the colors. Let's say you can double click here on the legend to only select one. Okay, I only want to see 5D, I double click, or I can click to select only one or the other. If I don't like the color, I can do some minimal customization down here. Say I prefer yellow, fine. Okay. And I can do a few more things. Okay, I can also look only at PDOS, for instance. So this would turn it around by 90 degrees. You only look at the PDOS or only band structure. Now I put back on. And you can also group orbitals by, for instance, here I'm grouping all the 5D orbitals of gold together. And also I have only one gold, so it's not very clear what's going on. But if I have a system with silicon oxide, I want to sum over all silicon, whatever orbital it is, and all oxygen, you can choose a different option here, and you can do different kind of groupings. You will see maybe later for the next tutorial. Finally, you can download this image as a PNG, or you can download the data underlying this plot, okay? And then you can open it. So for instance, the PNG, and I can open it, but I guess you understand what's going on, right? Final thing I wanted to mention, if you go back to the summary, so maybe just 1 second, stay in the summary, in the result here. Here you see something very interesting, what you would expect, no? Gold has 5D orbitals, okay? And these 5D are 5 bands, not very dispersed, almost flat, because again, the D are kind of still inside, but have some dispersion and interact with the orbitals. And the 6s of gold are this parabolic band, which then interacts with the D and continues up here. So you can start understanding a bit the kind of electronic structure of material, how the D and S orbitals of gold interact in a band structure. They originate from flat states in gold, but when you create a solid, they create a band structure. Final thing, you go back to summary up here. And here the 2 download buttons appear. You have 2 buttons. One is download raw data, and one is download the AiiDA file. The AiiDA file is the file which contains everything. All the inputs, all the outputs, all the information for the GUI. So if you download it, you can give it to another colleague in the same AiiDAlab GUI, they can upload it and see in the GUI. Everything is there, the full provenance. If you instead download the raw data, this is useful if you want to show this to a person who knows Quantum Espresso but doesn't want to know about AiiDA, because this downloads you a zip file. Okay. And if you open it, in it you have all the workflow and all the steps of the workflow. For instance, it was the relaxation workflow. We did 2 iterations, if you remember, one with a red cross and one which worked. And each of them had 2 inner steps. And you had inputs, outputs, and the pseudopotentials. Everything is here. And for instance, if you open the input file, you see exactly the input file that the app generated for you. So again, if you know Quantum Espresso, you would recognize this input file. If you know Quantum Espresso, you also recognize the output file of the calculation. And if you don't trust me, that's really when we run it. The time is because of is UTC. So it's really the calculation we ran a few minutes ago. Okay. Unfortunately, we are a bit late. Took a bit longer than I hoped. So I think we do the advanced part next week. So on Wednesday, because we only have 5 minutes. Maybe I'll just then take the time to show the other parts since we have 5 minutes. So next time we continue. Just so you know, the next time we will run essentially through these advanced tutorials. So if you're curious, you can already do them, of course, where we see how to set up advanced properties, change the K-mesh, change the pseudopotential, set a DFT plus U, change pseudopotentials, etc. But also how to set up a ferromagnetic system and how to set up an anti-ferromagnetic system directly in the GUI without having to go and change the input file. And then we go through these other tutorials. If you go back to the homepage, you can click here on the AiiDAlab logo. I'll show you just the additional buttons you have here. So what we run is new calculation, okay? The last one is just a link to Quantum Espresso. There are a few more things which are interesting. First, calculation history. Now you should have run 1 calculation. Maybe you start running 3, 4, and you say, okay, what did I run yesterday? You click on calculation history, and you get what you might expect, a list of all the calculations you ever run in this AiiDAlab instance. With some filtering, you can search by date, etc. From here, so you have 2 because I ran one a couple of hours ago, but essentially this is the one I ran just a few minutes ago. You have the label, that's why it's important to put a good label. You know, if it failed, you can delete it. Let's say I don't like it. Let me delete this one. I can go here and delete it. I can download the files as I did before without having to open it, or I can click here and I go back to the same page where I can inspect the results. So I just clicked while it was I show you. So this was for deleting. I have to type yes to make sure I don't want to delete it by mistake. Here, I clicked on this. If I refresh, just to show you, convince you I already deleted it. I refresh my page. And you will see 1 calculation was deleted. When I clicked here, I opened a new tab, which I'm going to open in a moment. And you will see I went back to my view. So again, here there's only 1 now because I clicked delete. And when I clicked here, I open a new tab and I can see again all my results, inspect them. So this is the calculation history. One interesting thing, if you don't want to run again, you want to see how it works for muons, and you don't want to run the muon simulation, you can go in the load examples. And we already run essentially all the interesting examples that we wanted to show you and a few more. And we exported with the button download AiiDA file that I mentioned before. So with those, you have a number of examples. So if you want, for instance, you want to see an example of muons, the stopping inside on lithium fluoride, or you want to see, I don't know, iron, ferromagnetic, benzene, etc., you can just click here and download it, for instance, import it. And just importing here, for instance, the indium arsenide bonds and PDOS. This worked. If I go back to my calculation history, I refresh, and you will see there is a new one. You just close a few windows, maybe. You don't get confused while it loads. This was the import function. Okay, now here I have an indium arsenide simulation. I can click on it. And you see here it says example because we properly labeled it. And it was run some months ago. Okay, so 30th of January. Something that one of us run. And when you go here, you get the results of what we run. Indium arsenide, you can look at the bond structure and PDOS, and you get the bond structure of indium arsenide. Okay, you can look at the PDOS again. Remember, DFT is not expected to predict correct gaps, so don't expect to have the correct gap here. Okay, that's not surprising. In principle, we shouldn't even do bond structures, if you remember correctly what Nicola told you, but somehow, since they kind of are okay, people typically do it, and it's a good starting point for higher level of theory. Okay, and finally, but this may be not so important, I just mentioned you, so we don't do it, we don't install anything, I'll just show you the last button, plugin store. It's a plugin of the AiiDAlab Quantum Espresso, AiiDAlab Quantum Espresso app. We pre-installed the one of phonons, muon spectroscopy and Baudel charge because are the one we wanted to show you. But there are a few more, and you can go here and install them if you want to try. Everything should work, but maybe focus first on the one we want to highlight here. Okay, final questions for today? The thick, sorry, I didn't tell you, right? That's the fat bands. So essentially it means that you take the projection on that band. So every band will have a contribution, can be a bit of 30%, in this case, I don't know, arsenic for S and 30% indium 5P, etc. And you put a thickness, which is at every point is proportional to that contribution. So if you go to bands, here you see there are multiple bands overlapping. You can, the magnitude is just a factor. You can decide based on what you want to see, okay? But helps you visualize immediately what the contribution, these are essentially our, well, I guess this is arsenic 4P, right? These bands have some contribution from, I imagine it's indium. We can check we can change the color if you want, but here the code selected the same color, so you can pick a different color. Yeah. That's one of the things you can do. If you really care, for bulk is not so important, but you can do here, group, no grouping. And here you get all the orbitals. If you, in this case, for instance, it's interesting to see group per atom, and it sums everything only on indium arsenic. So you can say, oh, these are really coming from indium, and these are really coming from arsenic. So it's actually a good example to see the various grouping options. Same thing for atoms. You can also, in case you have multiple gold, you have water, you can separate the two hydrogens or sum the two hydrogens. Okay, thanks a lot. So we stop here for today. See you in 2 days. For those of you who are here, coffee break, and then we are still around for another hour if you have questions.